So start illustration number 3 as shown in this figure. A long wire kept vertically on the plane of paper. So this is a long wire that carries electric current I, which is shown in the upper direction, and a conducting ring which moving towards the wire. So the direction of this ring is towards the wire with the velocity v and with its plane coinciding the plane of paper. So this is the direction. Now we have to find out the induced EMF which has produced in the ring when it is at a perpendicular distance r from the wire. So this is the distance from the center. Now radius of the ring is a and that is very less than r. Now first of all, with all these values I can find out the magnetic field, and hence magnetic field at a distance r from the wire carrying current that is given capital I. So the magnetic field of that is given by V is equals to mu 0 I divided by 2 pi r, where mu 0 is the permeability of free space, and that is having the value 4 pi into 10 to power minus 7. So with the help of this, now I can find out the magnetic flux linked with the ring, and therefore I am denoting it as phi. So what is the equation? Phi is equals to VA. Here A is the area of this ring and this ring is in circular shape. So the value of its area is pi r square. So phi is equals to V into pi r square. But here you see the radius of the ring is small a, and hence I am writing over here instead of pi r square, pi a square. Now, substituting the value of b in this equation. So, mu 0 I divided by 2 pi r into pi a square. So, this pi gets cancelled, and hence in the numerator mu 0 I a square divided by 2r. So this is the value of magnetic flux. But this is not the end. We have to find out the induced EMF produced in the ring. So therefore, is equals to epsilon, that is equals to minus d phi by dt. So substituting the value of phi in this equation, therefore epsilon is equals to minus d by dt into mu 0 I a square divided by 2r. Now here which are the quantities are similar, or we can get out of the differentiation. So the quantities are only mu 0 I and a square, and is 1 by 2. So minus mu 0 I a square divided by 2 into d by dt 1 over r. So 1 over r is having the differentiation of minus 1 upon r square. So the value of minus 1 upon r square, so this sign negative and the minus 1 upon r square sign negative. So the total EMF means the induced EMF is having sign positive. Therefore, epsilon is equals to minus mu 0 I a square divided by 2 was as it is, d by dt of 1 upon r. So it is minus 1 upon r square, but the differentiation of this r is still not completed. So that is dr over dt. That is equal to minus mu 0 I a square divided by 2r square. Now see, this negative sign is comes to the outer side. So minus into minus is plus into dr by dt. Here r is the position, as you have seen in the figure, actually the distance. So the distance upon time is velocity, and hence epsilon is equals to mu 0 I a square upon 2r square into v. So this is the final equation of induced EMF. Now see, any MCQ is given to you in which this current is given, the radius of the particle is given, and the distance between the body and the conducting wire is given. So you can easily find out the induced EMF. Starting the illustration number 4, it is stated as a conducting ring of radius r is placed perpendicularly inside a time varying magnetic field as shown in the figure. So this is the ring. Here is the north and south pole. So between the north pole and south pole, a ring with radius r is placed. The magnetic field changes with time according to, here the magnetic field is given at time t. Is equals to V, and that is given by V0 plus alpha t. Here V0 and alpha are the positive constants. So we have to find out the electric field. So first of all, if you remember that the magnetic flux or the value of magnetic flux, we can find out. So phi is equals to B dot A. Here again, ring is of circular type. So area will be pi r square, and here the radius is r. So B into pi r square. But the value of B is B0 plus alpha t into pi r square. Therefore, this is the value of flux. Now, according to Faraday's law, the EMF produced can be written as epsilon is equals to minus d phi over dt is equals to minus d by dt into B0 plus alpha t into pi r square. That is equal to, see, this B0 is constant, so its derivation is 0 with respect to time. Here t is coming, so pi r square will be as it is, and alpha t derivation with respect to time is alpha, and the negative sign you don't forget, it is as it is. So this is my equation number 2, and the above flux was my first equation. Now, by definition of the EMF, the work done by the electric field for one complete revolution of a unit positive charge on the circumference of the ring. So I can write down the work is equals to the electric field produces over the length of the body. Here E and dl are in the same direction. So the work is equals to E integration dl. This is the third equation. But here again, if you find out the length of the circle or ring, then it comes out to be 2 pi r. So I am directly substituting the integration of length. Therefore, integration E dot dl is equals to E into 2 pi r. Now, comparing the equation 2 and 4, we will get E into 2 pi r is equals to alpha pi r square. Here negative sign is neglected. You have to understand that. Because electric field is either in positive or negative direction, but at present our task is only to find out the value, magnitude of electric field. So it may be a positive or negative. Here pi is cancelled out. Therefore E is equals to alpha. Here 1r is also cancelled out. So alpha into r divided by 2. So this is the final equation for the required electric field. Now we will switch on to the illustration number 5, which is very easy. Illustration number 5. A field is given by vector A, xi cap plus yi cap plus zk cap. Can this field is used to obtain induced EMF, and one hint is given that a field should be a magnetic type to obtain the induced EMF. So we just have to check that the given field is a magnetic type or not. So for that, if the given field is magnetic, then we are consider over here that A field is a magnetic type. So its surface integration over the cross section means integration A, and if I am taking the cross section as seen in this figure, see, this particle P has been taken under the effect of this field, and it is in the 3 dimension, and the element is taken as dA. So this integration must be 0. So this is the condition should be satisfied. So now we have to check whether this condition is being satisfied or not. So for that I am considering this vector dA as a unit vector notation. So dA is equals to a magnitude and the direction in the form of position vector. Now if the coordinates of this point, as we have to consider it in 3 dimensions, so I am taking their coordinates of point P are x, y and z. So these are the coordinates. Now this is the vector which represents the actual position, or we can say the direction towards the point P. So I can consider this vector R as the similar of the given field, and hence my vector R is equals to xi cap plus yj cap plus zk cap. And now you have to find out the value of unit vector r cap. So for that I have the direction, or we can say the magnitude. Therefore r cap is equal to the vector upon its magnitude. So the value of is x over r I cap plus y over r j cap plus z over r k cap. Now surface integration over the surface, that implies integration A dot dA, and this is nothing but the surface of sphere, so I am only consider over here the surface because we have taken the sphere. Now the integration surface as it is, the value of A is xi cap plus yj cap plus zk cap into dA into r cap. In the r cap, 1 upon r is common from all. So 1 upon r, and again the same field vector xi cap plus yj cap plus zk cap. Now this 1 upon r is constant with respect to dA, means surface element, or you can say volume element. So I am taking it outside of the integration. So 1 upon r integration x square plus y square plus z square dA. Now this is the value comes from the dot product which we are already familiar from semester 1. So I dot I becomes 1, j dot j becomes 1 and k dot k becomes 1. But I dot j is 0, I dot k is 0, and here the dot product is taking place. So I have written it directly, but the concept should be clear in your mind. Now see, this is the actual value of r square, because r is equals to xi cap plus yi cap plus zk cap. So this is the value of r square. So can I take r square also outside of the integration? So 1 r will cancel. So only in the numerator there is a value of r, and that is r integration dA. Now what is the area of a sphere? So we have to take its integration, and that is equal to r into 4 pi r square. So that is equals to 4 pi r cube. Now see, here the sphere what we are taking, it is not possible with the zero radius, and hence this full quantity will not be zero, and so we can write one statement that the induced EMF cannot be obtained. So this position vector or the field vector which is given to us is not the magnetic type, and hence the EMF cannot be produced. Now we will switch on to illustration number 6.